Another equation that would be really handy to have is one that you don't have to have time for to solve problems where you're not given uh, time or you don't have any information about time. So we're going to develop an equation that eliminates time completely, gets rid of it, and just relates these variables, the starting and ending speed, the acceleration, and the distance, how far it travels. Now, to eliminate time, we're going to need to solve for it in an equation that we already know. And that equation could very well be acceleration is final velocity minus initial velocity divided by delta t. If we solve this for delta t, here's what we get. Delta t is Vf minus Vi over A. So, starting from this point, knowing that delta t is Vf minus Vi over A, we're going to plug that in to our standard equation that we just have been using, that we just recently developed. I'm going to switch to a different format here. It's a little more free-flowing. Well, let's first reiterate what we already had in the last slide there, and that is that delta t is the equivalent of Vf minus Vi over A. So we can eliminate time in any equation by just plugging this right-hand side term in for delta t. We're going to do that for this equation. The equation that we just developed, d is equal to Vi times delta t plus A over 2 times delta t squared. So let's do that right here. D is equal to Vi times delta t. Well, delta t we're now going to call Vf minus Vi over A plus A over 2 times delta t squared. But delta t now, remember, we're saying is Vf minus Vi over 2, and that's going to be squared. Well, this equation is looking kind of ugly, so we're going to have to get rid of A in the denominator if we want to solve this. Sorry, that's a mistake. That should be A, not 2. I don't know why I wrote 2. So let's multiply both sides by 2A. That'll get rid of the 2 here and the A here and give us something easier to work with algebraically. So 2 times A times D is equal to 2A times this term, Vi, which is multiplied by Vf minus Vi over A, plus 2A times A over 2. So that's 2A times the second term, times Vf minus Vi over A, that quantity squared. Let's slide down and give ourselves some more room. And now let's, I'm just going to rewrite this a little bit differently so it's easier to see what cancels here. I'm going to pull the A out of this term, so it's going to be 2A over A times Vi times Vf minus Vi plus, and I'm going to pull the A out here, but this A is squared, so I'm not pulling out A, I'm pulling out 2A squared. Also, A times A is A squared in the numerator, so I have 2A squared here, and I have 2A squared in the denominator. With that gone, I now have Vf minus Vi and that quantity squared. Looking at what cancels, A's drop out, but 2 doesn't here. The whole 2A squared thing goes away. So I can rewrite this as 2AD equals 2Vi times Vf minus Vi plus, that term's all gone now, so it's just Vf minus Vi quantity squared. Let's expand this. 2AD is, I'm going to distribute 2Vi among these two parts of this binomial here. So 2Vi Vf minus 2Vi squared plus, now I'm gonna just expand this. I'm going to complete the square with the good old-fashioned FOIL method. So it's Vf squared minus Vi Vf minus another Vi Vf, so minus 2 Vi Vf and then minus VI times minus VI would be plus VI squared. So now with this completely expanded, let's take a look at what we can collapse here, what we can get rid of. One thing we see is we've got 2VI VF minus 2VI VF. So that term disappears. And that's nice because that was kind of complex. What's left? Well, we've got negative 2VI squared plus a VI squared. Well, if you add those two together, that gives you negative VI squared, negative 1 VI squared. So 2AD is minus VI squared. So that takes care of that term, and then the only thing we haven't accounted for is this VF squared, so we'll add that, VF squared. What we really want to know is what's the final velocity in terms of the other variables here. So I'm going to solve this equation for VF squared by adding VI squared to both sides. Adding VI squared to both sides gives me this, 2AD plus VI squared equals VF squared. What I really want to know here is what is VF, not VF squared, because that's ultimately what we want to do is figure out what is going to be the end velocity of this thing if we know these other variables. So I'll take the square root of both sides. That will do that for me. So rewriting this just tells me VF is equal to the square root of VI squared. I'm going to put that term first because that's how it's usually written in like physics books and stuff, plus 2AD. All right, so there we have another equation that would be a good one to put in your toolbox. The final velocity of an object that's under acceleration is equal to the square root of what its initial velocity was squared plus 2 times a acceleration times the distance that it accelerated through. So here's that equation in the boxed in form. Again, boxed in equations that you see in these notes. Pretty smart idea to put those in your toolbox. Have them handy when you need them later. Like now. Here's an example problem that we can maybe solve using this equation. Let's analyze, plan, compute, and evaluate like we usually do. Analyze. The car is traveling 26.8 meters per second when the driver hits the brakes. Okay, so that's an initial velocity. VI is 26.8 meters per second. Driver hits the brakes, that means the driver begins to accelerate, negative, decelerate. Car comes to a stop. So implied there is the car comes to a stop. The final velocity is 0. It does this in 35 yards. Well, that's a distance. D equals 35 yards. Question, what was the acceleration on the car? So what we're trying to find here is A. To make a plan, as always, we're looking for an equation that links the stuff we know, these three things, to what we need to find, which is that. And the equation we just derived will do that. Final velocity is equal to the square root of initial velocity squared plus 2 times A times D. So this has all the terms in it that we're involved with. Final velocity, initial velocity, acceleration, which is what we're actually trying to find, and the distance, which is given to us. So part of my plan is going to be isolate the variable I'm looking for, which is A here. So I think before I'll do that, however, make my algebra simple, since VF is 0, I'll substitute for 0 here. 0 is equal to the square root of VI squared plus 2 times A times D. But 0 squared is also 0, so I'll square both sides, and that'll tell me that 0 is VI squared plus 2 times A times D. So if I subtract 2A from both sides, I get this, negative 2AD, I'm sorry, I'm subtracting 2AD from both sides, is equal to VI squared. So now I'll solve for A, which is what I want here, by dividing both sides by 2D. So VI squared divided by negative 2D is my acceleration. Okay, now I got a units problem here. Before I compute my next stage and plug my units in, I'm going to have to figure out what 35 yards is in meters, because my velocity here is in meters per second. So I'm going to do a little unit conversion. I'll do my unit conversion up here. Using dimensional analysis, a good tool for unit conversion. Do it right here. I've got 35 yards. There are 36 inches in every yard. That'll get me into inches. But there are 2.54 centimeters in every inch. That'll get me centimeters. And there are 100 centimeters in every meter. So that will get me the unit that's my target, which is meters. Let's grab a calculator and find this out. So 35 times 36 times 2.54 all divided by 100. Well, that tells us that my distance here in meters is 5.3 meters. So that's what I'm going to put in here for D. So now acceleration then is VI squared. Well, that's 26.8 meters per second, quantity squared, divided by -2 times the distance. And the distance we just figured out is 5.3 meters. Let's check our units. This is going to be meters squared over seconds squared. But one of those meters is going to cancel because I got meters down here. So this cancels with the squared part of the meters squared. And that's going to leave me with meters per second squared. And that is acceleration. So good acceleration units. So now let's do the arithmetic. Go to my calculator. 26.8 squared divided by -2 times 5.3. The answer that I get is about -68 meters per second squared. Now, you might look at that negative and say, what went wrong? That doesn't make any sense. But actually, it does make sense. If the car's forward motion is called positive 26.8 meters per second, and it came to a stop, the acceleration vector must have been in the opposite direction, which means negative.